The we all know stable marriages, and turns out a lot of interesting practical applications, including some of the stuff we've heard from the previous two speakers, fit into this formulation that I'm going to present. In contrast with other analyses that we've done, the community have done in the past, like for example, random ranking lists. Joint work with Hussein, who's over there. The outline is you look at dating sites or ride-hailing or room renting or any of these sort of matching markets, and there is two-sided in that. There's somebody selling something, somebody buying something, and then they're ranking each other in terms of preferences, right? So you go to one of these sites and you'll see some examples. Right? And this fits into a metric space formulation, and both in the continuous and discrete senses. There are connecting previous results, and I'll review that as we go along. So here's an example. If you go to OkCupid, you answer sort of binary questions like this. Okay, are you a morning person? Could you date somebody who is really messy? Do you like scary movies? Right? Is smoking disgusting? Is jealousy healthy in a relationship? Right? So you basically answer these binary questions. And then you, as the entrant, have your binary vector, and another person has their binary vector. Now it sort of makes sense to look at what Hamming distance, right? How many things do you agree on? That's an example, right? So that sort of automatically comes in here, but you can think of like you're listing your property on Airbnb, and somebody's trying to say, I want to go to the Olympics and I want to look for a house that's close to public transit or to these particular events and locations for these events, like swimming only. I'm very interested in that. So there's some preferences people are expressing, right? So that's the idea. Here's the formulation. So let's say there are n men and n women, and each person answers a binary, k-binary questions. And so their answer vectors take values in 0, 1 to the k, and you can think of distances between two of these vectors. Think of Hamming distance, which I've already mentioned. I'm going to introduce another metric where you look at the coordinates are sort of weighted. In Hamming distance, all coordinates matter equally. This one, let's say the coordinates. It could be a deal breaker if you like cats and she doesn't, or the other way around, okay? So that's what it means to, and whether their favorite color is blue or red may be less important, okay? So that's sort of how you should think of the second metric. And you'll see, if you don't think of it like that, then, OkCupid shouldn't be in business. The question here is how many questions do I need to answer before I find the right person for me, okay? And the metrics matter. So each woman ranks the men by distance from closest to farthest and vice versa. And when there are ties, which happens in discrete spaces, you break them randomly. Are you okay with this? And this is naturally how we do it, okay? We don't sort of flip coins typically, but there's a nice, wonderful model, but some of these practical questions, especially with matching markets, lead to this formulation naturally. I'm going to just assume every one of you, every one of us knows stable matching, so I'm not going to spend too much time reviewing it. In ride-hailing, for example, is very similar. There are people who want cars, and there are cars running around available to be hired. And here the metric is naturally something like Euclidean distance. It's a good proxy for time to pick up, okay? But if you talk to guys like for folks who do this for a living at Uber, it's not so much that for a given person, how many cars are nearby and what's the time to pick up. The orientation of the vehicles on the streets matter. Not that they're necessarily in a one-way street, but actually the orientation of the vehicle on a two-way street matters, okay? You can do this for amusement, like in New York City where you live. You can do, not you. You're in Boston. So Siamak lives in New York City. Your collaborator, sorry. So if you stand there and open your Uber app on a one-way street, and wait until the car is just past you, because the guy can't turn around, and then ask, sometimes the guy will get assigned to you. Meanwhile, there's a guy behind on the right side of you from the street's perspective, but they won't get assigned because they're not quite yet Euclidean distance is still ruling this world, okay? You can do this just for amusement. And this guy will take 8 minutes to go round, and come back, okay? Whereas this guy could have been assigned to you in 3 minutes, okay? So this sort of a thing, has seriously interesting practical consequences when you think of these problems, right? Here's a list. So it's very most of the So this is the Web 3.0 world, right? 1.0 is all information networks, 2.0 is, well, 2.0 is information networks and social networks and so on, but this is the third generation. So lots of stuff being bought and sold in these different places. So what I'm presenting to you is actually preliminary analysis. You'll see that there's a lot of things that, very obvious what further work looks like. We're going to consider stable matchings in discrete and continuous metric spaces. We're going to consider the discrete space I showed you with the two distances that I've given you. And then for continuous spaces, we're going to look at the Euclidean distance on R. You can look at higher dimensions as well. In your minds, you can already start thinking of this as, you don't have to think of particular spaces like, 0, 1 to the k, like the hypercube. You could also think of, or the real line. You could think of just points on a graph, and men are on some vertices and women are on some other vertices, or sometimes they're the same vertex, and then you want to use the graph distance and number of hops, for example, to match. Okay, and that models also things where it really is, a lot of these guys who are online stores, like think of Alibaba or Flipkart or someone, or even Amazon. If you want to sell a certain brand of shirt and you don't have the purple colored version of it in San Francisco, no point in showing it to San Francisco guys, because it's going to cost you a lot of money to ship it from, let's say, LA or Denver or wherever it is that you have it in stock. Okay, so this is a locational thing matters. Okay, so that's questions that come up are, when is there a unique stable match? Because now we're not sort of flipping coins. That's what I mean. Rather, we are ranking each other based on preferences. So that hopefully, things should be unique more easily. Okay, without resorting to tie breaks. What is the probability that a woman matches with a top choice? This also hopefully improves. Because I've taken the trouble to answer all these questions, so hopefully, what I mean in the random ranking list case, even in the man optimal, so the n men, n women, all the ranking lists are drawn uniformly at random from a set of all permutations. In that case, even the man optimal matching, a man doesn't get his top choice. The choice to start, where the man optimal matching matches you with is men get matched to somebody around roughly log n on their preference list. Okay? So hopefully here, because of all these preferences, you can do better, okay? And also, how many questions do you need to answer? Okay. Continuous model, there's been previous work by Holroyd, Perez, Schramm, and one other person. I guess you should say three names in the et al. For the last person. I don't remember the name, okay? But they've considered matching Poisson points both in 1 and higher dimensions on the real line, and R2, etc. And then the question is, what's the distance? You look at a stably matched pair, pick an edge at random from the stable matchings, and ask what's the expected distance, etc. Okay. So here we're going to look at this in the unbalanced case where the Poisson processes have different rates. So this is just useful to review. The most important thing is this last definition. When there are multiple stable matchings for a person, and let's say a man and a woman are matched in at least one stable matching, then they're going to be called stable partners. So a man can have multiple stable partners and vice versa. So that's a quantity of interest. Okay. A very nice paper by Patel, actually a couple of papers, where he showed that the average number of stable matchings when the ranking lists are drawn at random is this quantity. Okay, it's like n log n roughly, and then and the average number of stable partners is log n. So you actually have lots of stable matchings and lots of stable partners. A surprising result by Ashlagi et al. Recently is that if you have even just one additional person of the opposite gender, it could sort of vastly reduce the number of stable partners. It's not clear yet how that collapses a set of stable matchings, but surely it does. But it hasn't been quantified. But this is already very interesting and surprising. So it seems like some sort of imbalance makes a choice go away. In one case, not so nice way. In the other case, nice way. So who is in the short supply just benefits. let's look at our situation where we have, I'm going to start with 0, 1 to the k, and then with Hamming distance. I'm just going to quickly walk through what happens when k equals 1. Okay. Initially, each man, so let's walk through the algorithm. Each man or woman has independent and random ranking lists, just to begin with. And then each person picks a 0 or a 1. Okay. And a man who picks 0 moves all the women who picked 0 to the top of his ranking list, leaving the order unchanged. So initially, I ranked all the women randomly. And out of these n women, some number n0, let's say, picked 0. And wherever they are in his ranking list, he moves them all ahead of all the guys who picked 1, leaving everybody else's, leaving the 0, the ordering between them unchanged, and the ordering between 1s unchanged. Are you okay with this? So the tie-breaking rule is implicit. Similarly, the men do the same thing. Men who picked 1 do the same thing, and then women too. And with ranking lists so rearranged, we look for stable matchings. Okay. So the number of, again, walking through this, right? The number of men who pick 0 is n over 2 plus minus square root of n. Okay. So if you look at all the men who picked 0, roughly half of them will pick it, but there's this fluctuation. Now, let's assume, without loss of generality, that men picking 0 is smaller, the number of them is smaller than the number of women picking 0. So this is in the unbalanced case for all the men who pick 0. There are fewer of them than the women who pick 0. So it's n, some number, let's say, k, and k plus l. Okay? So these guys, the ranking lists are still random once, you've conditioned on this. And the Ashlag et al. Result will apply, and then you'll get the number of stable partners for these guys goes to 1 with high probability, okay, as n goes to infinity. Same thing will happen if you apply. So if the number of men who picked 0, is smaller than the number of women who picked 0, then the opposite is true for the 1s, because the total adds up to n, right? And still it's random, and the same exact thing will apply. Then that leaves us with the men who picked 1 and the women who picked 0 who still aren't matched. When they look at each other, that is also still random, right? That is, this is the residue of the phase 1 of the algorithm. And the Patel results will apply, and you'll get multiple stable partners and matchings as quantified by Patel. So the conclusion is for k equals 1, there's no uniqueness of stable matchings, and tie-breaking is needed to get stable partners. So the question is, how far do I need to go with k? So if k is log n, okay, that's a natural place to ask, because now you have, k equals log n means you have 2 to the k, or the number of answer vectors is n, order n, right? And it still doesn't help because of Hamming distance. I just need to agree with you on some, if you have 2 random binary vectors of length k, they will agree roughly on 50% of their entries plus this fluctuation. So it really doesn't help, okay, yet. So k equals log n isn't sufficient, you can get that result. On the positive side, we can go as far as, if you're willing to go as far as k equals n to the 6 log n, you can show, first of all, that the ranking list can be strictly ordered using Hamming distances that imply that there's a unique stable matching. But we think that the answer is somewhere closer it's not into the 6th. Again, now this is where, a site like OkCupid won't survive because there's way too many questions, right? But here's a pleasing thing, which is that each man or woman will be matched to their top choice with probability at least 50%. Okay, this is great on the one hand, which is completely false otherwise. Like in the random ranking list case, this probability is 0. So sketch of proof, let's just look at how this first thing plays out, part 1. So let's just take k equals log n, therefore specifically n equals 2 to the k. So now we're thinking of some, k-dimensional hypercube, and I'm dropping n men and n women on the vertices of this high-dimensional hypercube, k-dimensional hypercube. And so since there are exactly n vertices, and I'm dropping n men randomly and n women randomly, it's like I'm dropping 2 n balls into n bins, where one is, let's say, colored blue and the other one's colored red. There's a positive probability that there's there's a positive density of bins with exactly 2 men and 2 women in them. Yeah, that's easy to see. And because we're matching based on distance, the probability that there are 2 stable matchings, because once you fall in the same place, I still have to break the ties randomly. You can work this out. The probability that, in the 2 by 2 case, that there are 2 stable matchings, right, is 1 over 8. You can work this out. Okay. So there's a positive density of. So a person can have at least 2 stable partners with positive probability. So this log n doesn't suffice already. But the more interesting thing is that there are exponentially many stable matchings, because there's a positive density of bins that have the possibility of 2 stable matchings. That's enough to get you, and they're randomly, so you can see how, everybody see what's exponential, right? On some vertices, on several vertices, there are at least 2 stable matchings possible, and which way they flip, either the through stable matching or the cross stable matching is independently done. So you have exponentially many matchings, stable matchings, okay? So log n doesn't work, but as I said, n to the 6th log n will work, but for the strong reason listed in bullet 1, which is that you can uniquely order all the people. Okay, there won't be any coincidences in distances. Okay. So this is where the uniform metric is interesting. Not all questions are equally, important, or there's some serious deal breaker questions. And if you look at that metric, then as soon as k equals 4 log n, you will get this property of this ranking list being able, you can order them uniquely, and then there's a unique stable matching. Okay. And I'm going to go on to the continuous case. Do you have any questions for me right now? There are other generalizations I'll come to. This is an interesting thing. I've never seen a chair show a mobile phone announcement of how many minutes are left. Okay. So stable matchings on the line, unbalanced Poisson matchings. So here, let's take this ride-hailing application because it is, in a sense, roughly canonical. Okay. There may be other places. I have a feeling that the property rentals thing is certainly. Some people want to stay close to work. There are other metrics that play a role, but this is very direct. Okay. You can look at a 2-way street. Okay, so that means a car can be picked up. A car can pick up a hailer on its right or on its left. That's allowed. Okay. Or you can look at the one-way street. Okay. The reason I'm showing this is that this is exactly a certain type of queue, like a stack type queue. And you can analyze this. I mean, the analysis of this is known. So this implies bounds on this, very straightforwardly. Okay. And so the model itself looks like there are blue points, which are Poisson with rate lambda, and red points with rate Poisson with rate mu. Think of mu is strictly bigger than lambda. Okay. And here's a stable matching. Here's what it looks like, the 2-sided thing. You can match, a blue point can match either with the left on the red or on the right, depending on who was closest and available. You have to match with, hasn't been taken yet. It's not hard to see that there's unique matching on the real line. It's not hard to see. And there's a simple algorithm put out in the Holroyd paper, which is actually nice. Every point shoots out arrows, rays that emanate from these points, growing at unit speed with time. And if a ray hits from a blue point hits a red point that hasn't been taken yet, then they're the right guys to match. Okay. And if this blue ray hits, so for example, this blue ray starts, one on this side, one on this side. By the time it comes to this red got taken, because in an earlier time this guy got there. It keeps going and then it gets this. Okay. And you can see this algorithm terminates pretty straightforwardly. So let's pick a blue point at random and look at the distance to its partner on the line. Let's call it the matching distance. Now we're interested in how is this random variable distributed. Okay? In particular, what its expectation is, but also its exact distribution if we can get it. So for lambda equals mu, like I said, there's this paper by Holroyd et al. From 2009, where they show in the one dimension case, expected value of square root of x is infinite. And as you go to higher dimensions, you get good moments. Okay. This is infinite, but they can show in other words, expected value of x is finite, but at a higher value of t, it's not. That's what this is. Okay. Sorry, I didn't tell you when it was finite. Okay, this is just showing when it's infinite. Okay. Let's make this point I made earlier about, let's start looking at the unbalanced case, and I'm going to consider the one-sided matching problem. So my blues are still in rate than my reds, but I'm going to stipulate that blues can only match with reds on the right. If a red is available to you, that's closer to you, like for example, let's think of taxis or cars as blues and passengers as reds. This guy has somebody here, but the street is going this way, so you can't pick that person up. Okay? So this guy has to pick up this person. Okay, everybody okay with this? So this is exactly, this is just it's isomorphic to a last come first served prime to resume queue. It's identical. Okay, it's not difficult to see, but the way you should think of it is like, let's assume that this is the arrival to such a queue, and before this was served, another arrival showed up, so this one takes precedence, and before this got served, another arrival showed up, so this takes precedence over this, and hence that, and then this got served, and then this came up to the top of the stack, and it got served, and so on. Do you see this, right? So the nice thing about this last come first served queue is that everything is known about it, everything possible. Okay, it's stable when lambda is less than mu. The arrival rate is smaller than the service rate. It's stable, and you know all sorts of quantities. Okay, so now here's the formal definition. Just want to introduce one term here called the busy cycle. The amount of time that the queue is actually busy continuously, which in this case is when a customer arrives. It starts the instant this customer arrives, and then arrives an empty queue, and then stops. The busy cycle stops only when that person departs. Right. So think of a blue that arrives in an empty queue. They start a busy cycle, and the busy cycle ends when the blue leaves. And it's right. The second thing is because it's last come first served. Are you okay with this? So everything is known. In particular, this mean is 1 over mu minus lambda. So we're going to have some occasion to return to this particular value. So here's the theorem. For our two-sided matching, this random variable x, which we were interested in, it stochastically dominates the minimum of this b1 and b1 prime, which I'll tell you what they are. They're actually, they're distributed as the busy cycle of this queue. Okay? So there's a busy cycle of this queue, and then let bi be distributed as iid, bi and bi prime, as the busy cycles of this queue. And is in turn dominated by the maximum of these things, where again, these are the same bi's, but these n1 and n1 prime are just independent geometric random variables. Okay? So this bound looks, on the one hand, is encouraging to have bounds. On the other hand, you say, well, let me just compute the expected value and say, how does that look? So as a corollary of this upper bound, you can get this result that says the expected value is bounded by this quantity. Okay? But then you can separately prove through a combinatorial argument, okay, which is, this argument is quite interesting, as is this bound quite interesting. Okay, just in terms of mathematically what's interesting in this work is this one. You can actually get this better bound, okay? But we actually conjecture, so keep in mind that, so this is the two-sided stable matching, and we're now saying that you and your stable partner are not separated by more than 2 over mu minus lambda. Whereas for the one-sided stable matching, we already saw that value is 1 over mu minus lambda. I call attention to it, right? So just doesn't sound right that the two-sided guy is worse than the one-sided guy, okay? Because this is just more choice. So we know this bound is loose. But if you further think about it, let's just see what happens in the limit as mu gets very large. What does that mean? There are these blue points, and they're trying to match with a red point, either closest red point on the left or right, depending on availability. But the number of reds is increasing. That's what it means for the mu to keep on going. Let's say it's going to infinity. At some point, for every red point, it'll either match with the blue on the left or a blue on the right. I mean, there's going to be for every blue point, I apologize. Okay, the blue and red guy. For every blue point, when the number of reds is very high, there's going to be somebody immediately to his left or right that's going to match with. Okay. So you expect that this is actually much better than this number. Okay. And in fact, it should look asymptotically something like 1 over 2 mu, for the same reason I just told you. Okay. And we conjecture that this is the case, that you can actually reduce this bound by a factor of 4. It hasn't been done yet. Maybe that's okay. And you can just see if this even holds up in simulation, and it does. Okay. So that's for the distances and how they, how far they need to go to find somebody. Okay. But what about how far they are on your ranking list? So as we saw for the Hamming distance, you'll match with your top choice with at least 50% chance. But what about here? For the one-sided matching, everything about this is known, everything, right? Because I'm an arrival, I come to a queue. Now whether I match with my first, the next service token to arrival releases me, or the one after that, just comes down to whether there's an arrival after me or the service arrives before that. Everybody okay with this? And that's exactly equal to mu, which is the rate of the service, divided by mu plus lambda, which is the rate of both added up, right? And so everything is known for the queue. So for the last come first served queue, this probability is exactly mu divided by mu plus lambda. And you expect that you should do better in the two-sided case. And what this is showing you is that's true. X-axis mu is increasing. Y-axis is what's the probability of matching with your top choice for that given mu, holding lambda at 1. Okay. So you see that this is for the two-sided problem, and this is the one-sided problem. And obviously two-sided is better. Okay. And so there's an obvious lower bound which you can use. But again, you have to establish that the bound is actually mathematically correct. You sort of think, well, that should be obvious, but you think, oh, there must be some coupling somewhere. We haven't found this, okay? So it's very interesting, okay, problem. And I want to conclude by just saying that, this stable matchings in metric spaces seem natural, and they capture all these buyer-seller preferences. I also think in terms of practical applications, the ability exists here for looking repeatedly. I don't mean the dating case. Hopefully you're not dating like you're buying goods on Amazon, okay? Just, 5 times a week or something, okay? But just think of, when someone's repeatedly visiting and as preferences are being understood and revealed, my feeling is that this actually, there's a component of learning to this preference list, and they keep differing. Okay, and I think that's useful to understand and learn. And we've seen that theory differs pretty significantly from what happens in the random ranking list case, and therefore it's worth looking at this further. We've seen some basic stuff in this discrete model. It'd be nice to sort of think more generally, but also extend this to general graphs. And unbalanced point process matchings in higher dimensional spaces. I think at the moment I think of this as like sort of interesting theoretically, but who knows, right? When I remember Yuval Perez telling me, Poisson matching, take a look at this paper, and I did. And it never occurred to me that it has anything to do with practice at the time, but obviously it does. It's all ride-hailing. So I think Perez and all wrote this paper in 2009, while Uber started in 2009. They didn't know about each other. Happened to be the case. So I think the incorporating monetary and economic considerations actually, this is what I meant by when you see something happening repeatedly, it's very interesting. So there's an imbalance, there's more taxis than passengers or the other way around. There's serious economic implications. And putting the outer pricing loop on this sort of matching problem is very useful. Okay, and I think that is where, actually that's what Hussein and I started with. So we model all this, and then, wait a minute, and then we got, so we sort of peel the onion and come in now, and we need to put the other layers back in. Okay, thanks.
Let's take the questions offline. Let's thank all the speakers of the session.